the technology behind hypersonic missiles explained. Imagine a weapon that can cross 1,000 kilometers in minutes and change direction while doing it. No predictable arc, no easy warning, just speed and uncertainty. That's the promise and the problem of hypersonic missiles. They're reshaping defense strategy across the globe, and today, we're breaking down the actual science behind them. Not the headlines, not the hype, the engineering. Let's get into it. What is a hypersonic missile? So first, what does hypersonic even mean? In simple terms, hypersonic speed is anything above Mach 5. That's more than 5 times the speed of sound. To put that in perspective, that's over 6,000 kilometers per hour. Fast enough to fly from London to New York in under 45 minutes. But here's the thing. Not all hypersonic missiles are built the same way. There are two main types. Hypersonic glide vehicles, or HGVs, are launched by a rocket high into the atmosphere. Then they separate and glide the rest of the way, unpowered, skimming along the upper atmosphere at incredible speed. Then there are hypersonic cruise missiles. These are powered through their entire flight, using advanced air-breathing engines to sustain hypersonic speed at lower altitudes. Same speed class, very different flight profiles. How do they work? Let's talk mechanics. At the core, 3 things define hypersonic flight: speed, maneuverability, and, for some designs, advanced propulsion. Speed alone isn't new. Ballistic missiles have reached hypersonic velocities for decades. What's different here is maneuverability. Traditional ballistic missiles follow a predictable, arching path. Hypersonic glide vehicles don't. They can shift course mid-flight, weaving through the atmosphere in ways that make tracking and interception dramatically harder. Then there's propulsion. Some hypersonic cruise missiles use a technology called a scramjet, short for supersonic combustion ramjet. Unlike a traditional jet engine, a scramjet has no moving parts to compress air. Instead, it relies on the missile's own extreme forward speed to compress incoming air before combustion. Sounds simple. It is anything but. At these speeds, air is rushing into the engine faster than sound itself, and combustion has to happen in milliseconds, in a chamber where the airflow never even slows down. Engineers sometimes compare it to lighting a match in a hurricane and keeping it lit. This is precisely why hypersonic technology remains one of the most technically demanding fields in modern aerospace engineering. Why are militaries investing in them? So why the massive investment? Why has this become such a strategic priority? Reduced reaction time is the big one. A weapon that travels this fast compresses the window for detection, decision-making, and response down to just minutes, sometimes less. Then there's range and speed combined. Hypersonic weapons can strike distant, high-value targets far faster than conventional systems, without needing forward-based launch platforms nearby. There's also the matter of interception difficulty. Most existing missile defense systems were designed to track predictable, arcing trajectories. A maneuvering hypersonic vehicle breaks that assumption. It doesn't fly where you'd expect it to. And finally, strategic deterrence. In defense planning, the simple existence of a capability can shift the balance of power, regardless of whether it's ever used. It changes what adversaries have to plan and defend against. Engineering challenges. Now, building something that flies this fast isn't just difficult. It pushes against the limits of materials science. Extreme heat is challenge number 1. At hypersonic speeds, air friction generates temperatures that can exceed 2,000 degrees Celsius on the missile's outer surface, hot enough to melt most conventional metals. Guidance is challenge number 2. At these velocities, a guidance system has to process sensor data and make course corrections in fractions of a second, all while the vehicle is surrounded by a layer of superheated, ionized air called a plasma sheath, which can actually interfere with communication and tracking signals. Then there's material science. Engineers need composites and alloys that can survive extreme heat and extreme mechanical stress, without adding so much weight that they compromise speed or range. And finally, testing complexity. You simply can't fully replicate hypersonic flight conditions in a lab. Wind tunnels can only simulate these speeds for seconds at a time. So real progress often depends on actual flight testing, which is expensive, complex, and slow. Future outlook. So, where does this go from here? Research into hypersonic technology is accelerating globally, with efforts focused on improving thermal protection, refining guidance systems, and developing more efficient propulsion. At the same time, Defense planners are racing to develop counter-hypersonic systems, new radar technology, faster reacting interceptors, and space-based tracking designed to detect these threats earlier in flight. It's shaping up to be a genuine technological back and forth, offense and defense evolving in response to each other, in real time. Conclusion. So that's the science behind hypersonic missiles, how they fly, why they're so hard to build, and why they matter for the future of defense technology. Do you think hypersonic missiles will change the future of defense, or will new defense systems eventually catch up? Let us know in the comments. Thanks for watching. And if you found this breakdown useful, subscribe for more deep dives into the technology shaping our world.